Hello everyone. This is the Falcon probe, and it makes debugging your car, your AC unit, your home Wi-Fi router, your old factory CNC router, your floor heating controller, your pick and place machine, and everything in between so much easier. And it's completely open source. It's an all-in-one dev board and USB to CAN, serial, RS-422, RS-485 adapter, and if some of those letters and numbers sound confusing, let's dive right in and clear up some of that. All of these acronyms are about how devices talk to each other. Some define how data is formatted, others define how electrical signals travel across wires, and some define full communication networks. The Falcon probe is designed to sit in the middle of all that, acting as a bridge between your computer and real-world hardware. We'll start with the simplest layer and build up. At the core of many devices is UART, or Universal Asynchronous Receiver Transmitter. UART is a simple way to send bytes one bit at a time using timing, start and stop bits to frame the data. It usually runs at logic levels like 3.3 or 5 volts and is meant for short connections. You very crudely just define what speed you'll be running at and wait for the line to go low. And then you start counting bits at that speed. And the line goes high after the byte has been sent, until it goes low again for the next byte, aka the start bit. You'll find the serial UART inside microcontrollers, talking to GPS modules, debug ports on development boards like Arduinos, communication with Bluetooth or Wi-Fi chips. UART is great for simplicity, but it doesn't travel well over long cables or noisy environments. That's where the RS standards come in. RS-232 you might have heard of, since it's the classic serial port standard introduced in 1960 that many older computers and industrial machines use. And it's also the subject of an older project of mine called the Universal Serial Adapter, which might have been a bit of an exaggeration since the Falcon here might actually turn out to be even more universal, or at least more versatile. But if you need to talk to an old IBM PC, the Universal Serial Adapter might be closer to what you need. Like the other RS standards we'll talk about today, RS-232 is only an electrical standard. It takes the UART data and sends it using larger voltage swings and single-ended signaling. It's still point-to-point, one device talks to one device. You'll find it in legacy computer equipment, modems, terminals, lab equipment and such, but actually it's a standard you won't find on the Falcon, because I already made the Universal Serial Adapter for that. You will find the next item on the list though, RS-422. RS-422 upgrades the electrical layer by using differential signaling. Instead of measuring voltage against ground, it measures the difference between two wires. This dramatically improves noise immunity and allows much longer cable runs. RS-422 is often used in factory automation systems, long-distance wired sensors, and it's typically rated at 10 megabits per second, which is pretty cool for two pieces of wire wrapped around each other. It supports one transmitter talking to multiple receivers, which is useful for distributing data from a central controller. But if you need two-way communication, you need two pairs of wires. Next in line, RS-485 takes the differential approach of RS-422 and allows multiple devices to share the same bus. And it's electrically compatible with RS-422 besides the fact that it can turn off the transmitter and listen on the same pair of wires in half duplex mode. Devices take turns transmitting over the same pair of wires. This makes RS-485 ideal for distributed systems where multiple MCUs need control. You'll see RS-485 in building automation, heating, ventilation, air conditioning, factory machinery, pick-and-place machines, and generally very industrial applications, typically using protocols like Modbus on top of the electrical layer. RS-485 and the other two we mentioned defines the electrical layer only. The communication rules come from higher level protocols. On the Falcon, you'll find two SP3485 type transceivers for handling both RS-422 and RS-485. Technically, they are RS-485 transceivers, but since RS-422 is electrically just RS-485, where the transmitter and receiver never change sides, I've put jumpers to manually put the Falcon in RS-422 mode by disabling RX on one transceiver and enabling it on the other instead. This can be adjusted in software too, of course. More on that in a bit. The important thing to remember here is there's technically no difference between a transmitting RS-422 node and a transmitting RS-485 node, except sometimes the receiver is left on for RS-485, which will echo back whatever is transmitted. If it was a real hardware RS-422 only transceiver, that wouldn't be possible, as it cannot listen on the transmission line. And then it would typically have 2 lines for TX and 2 lines for RX in the same IC, opposed to here where RS-422 is split between 2 ICs. Making boards like these isn't easy to do in my garage, so I'm super happy to get this video sponsored by JLC PCB. JLC PCB offers super easy, reliable and affordable PCBs and assembly. Getting the finished product delivered after just a week means it's easier to iterate over a design and avoid multiplying risks by combining mistakes that are harder to fix later. Getting everything right on the first try is rare, so knowing that a mistake doesn't mean waiting a month for a new PCB is such a relief. And you're not just stuck with simple 2-layer PCBs and restrictive design rules either. With JLC PCB, you can grab a $30 coupon for your first 6-layer PCB order and get a PCB for just $2. If you're a new customer, you even get $123 of new customer coupons. If you're serious about improving your product development, I can genuinely recommend JLC PCB to get your product out the door faster. Finally, the Falcon has one more transceiver on board, which you probably never would have guessed is for CAN or CAN bus. Whereas RS-232, 422 and 485 only define the electrical details for transmission, CAN also defines the framing and protocol, which means it can't meaningfully just be slapped on top of a UART. That means it usually needs hardware support for CAN packets in the microcontroller itself. Most CAN systems use a dedicated CAN controller peripheral inside the MCU that handles message framing, arbitration, checksums, and automatic retransmission. That controller is then connected to a CAN transceiver chip, which converts the logic level CAN signals into the differential voltages on the bus. A good example of a whole ecosystem built around this is from Bosch, which originally developed CAN for automotive applications. The protocol was designed from the start for noisy, safety-critical environments where reliability and deterministic timing matter. Security-wise though, we've seen examples of car thieves unlocking and starting cars simply by smashing a headlight and injecting messages on the CAN bus. So, for better or worse, you can do a lot of things if you have physical access to the physical CAN wires on a car, but you should expect modern vehicles to separate security-critical systems from the headlight is broken or the tire pressure is low sensor. For the CAN transceiver, I've used the venerable SN65 HVD230, which converts logic levels to differential CAN signaling. Since we also need an MCU that supports both CAN and USB at the same time, I've picked the STM32F042, which by chance is already supported by the open source Candlelight GS USB firmware. I'm happy I didn't have to reinvent the wheel for this one, but I did have to fork it for one reason. Since it uses GS USB, which is natively supported by the Linux kernel, it'll show up in Linux as a CAN device right out of the box. But unfortunately, that means we can't use the RS-485 transceivers at the same time. Well, kind of, anyway. Since they depend on the MCU being enumerated as a USB to serial adapter and making it into a composite device supporting both is complicated, and it won't have the bandwidth for both at the same time anyway, you have a couple of options. You can either use my fork of Candlelight GS USB and use a jumper to switch between CAN and USB to serial to RS-485 mode, or you can simply flash the stock Candlelight GS USB firmware when you want CAN and a USB to serial firmware when using RS-422 or RS-485. Or if you want to get really crazy, use a separate USB to serial adapter and use all 3 transceivers at the same time. So let's say you built the Falcon using the production files on GitHub or ordered it from my webshop. How do you actually use it? If you bought it from the link in the description, I'll make sure it comes with firmware supporting both UART, CAN, RS-422 and 485. And if you build it yourself, you'll have to flash it using DFU util. The cool thing about the STM32F042 is you don't need a separate programmer to change the firmware. All you need is to change a jumper and plug it in. So you only need a programmer like an ST-Link if you want to do debugging of the code. To use RS-485, you simply use the 3-pin header on one side, and to use RS-422 in full duplex mode, you use the one on the other side as well. For this test, I've just left it unpopulated because I don't have a screw terminal or one of the other common connectors for a twisted RS-485 pair. But we can still test it by opening up the UART on the computer and tapping a few keys. Unlike UART, we see both a signal that looks like it and another one that's the opposite polarity. As we can see on the scope, the protocol is super simple. Just the UART data represented as a differential pair. If we do the same test to see if CAN works, I've started a transmission on the computer, we see a weird differential sawtooth wave, which is not exactly what we want, and certainly not a complete CAN frame. CAN is designed to be super robust, so what we're seeing is the CAN peripheral on the STM32 detecting an error condition, immediately aborting and trying to send an error frame, and failing again. The reason it's failing, of course, is there's nothing connected to it, and the line is completely open, so it can't even detect the frame it's trying to send. But it will keep trying. So if we insert a terminating resistor, which would usually be 120 ohms, along with the probes, we should see things improving. Of course, I also left a pad on the board for the resistor. The reason I haven't populated it by default is not all CAN nodes need it. Since CAN is meant to be a transmission line terminated with 120 ohms at each end for a DC line resistance of 60 ohms. If we kept adding more resistors in parallel, we'd get in trouble from the line load being too high eventually. So how do you use CAN with a laptop? I could have hooked a Falcon up to my car or a device at my day job, but for simplicity I've just hooked one up to a laptop and the other to a Raspberry Pi. Since CAN over GS-USB is Linux native, the device already shows up as a network interface on both. In Windows Subsystem for Linux, it's not compiled in though, so beware of weird kernels. And you can either use CAN using Python, C, or your programming language of choice. But again, for simplicity, I'm using the common CAN utils package. It's in most major repos, but also compiles easily from source. By running CAN dump on one and CAN send on the other, we see packets going through at a default 1 megabit baud rate. I haven't tried to see how fast it'll go, but for CAN that's usually not the point anyway, as you probably want to communicate with something else already in place with this. I did make a little mistake on the first version, since I just copied the D-sub9 connector from the universal serial adapter. But the footprint for that is actually a female footprint, meant to plug straight into a male connector like this. So you can use it without a cable. The same goes for the Falcon, but the problem is there's already a loose standard for CAN dongles like this to have a specific pinout. And hooked up like this, that's mirrored compared to most other dongles already on the market. The quick fix for that is to mount the D-sub9 on the bottom instead of the top. That can be a bit confusing, so I've changed the pinout on GitHub already. On my shop, I'll be sure to indicate clearly what pinout you're getting. Besides the revision number, it's also pretty easy to see because I changed the name too. It turns out it's incredibly hard to have an original thought in this world. Originally, I intended to call the device the toucan probe, so I googled that and didn't find any conflicts. Until I had the whole thing manufactured and then found out that not just one other CAN dongle, but 2 others had used that name. So if you think Falcon is a bit weird, sure, but the other bird was already taken. So if you have a board that actually says Falcon on the back, you can assume it's the industry semi-standard pinout. I'm really happy with how this board turned out. Not just because it's a cool adapter with transceivers for the electrical standards that a microcontroller doesn't support natively, but also because it's an amazing dev kit to have in my bag, as I can reflash the firmware to anything I need in seconds, even if I forgot the ST-Link. I've only scratched the surface of what it can actually do, so maybe you'll see a few follow-up videos on this. Either way, thanks for watching.